In this lecture, we will probe how we excite collective states in nuclei and how we probe them using electromagnetic probes. So, this is done by Coulomb excitation or inelastic scattering, photoabsorption, and to look at the decay gamma rays which come about when you make a compound nucleus in low energy fusion reactions. By low energy, I mean roughly 5 MeV per nucleon and heavy ion collisions with the target. So then you produce a compound nucleus, it evaporates neutrons or protons, alphas and so on, and then comes down in excitation energy and emits, because now it cannot emit neutron, proton, alpha, then it will emit gamma rays. So we study these gamma rays with high resolution spectrometers. The other way we look at these collective excitations is so-called giant resonances in nuclei, and they are of the electric type and the magnetic type. So we have E0, E1, E2, and then M1 and so on. And of course, they have also isospins, so there are isoscalar transitions, isovector transitions, and so on. We will also look at some rare electromagnetic processes, and we will take a few examples of that, namely two-photon emission. This is a higher order process. Of course, it is much rarer than single photon emission. Then we have pair conversion. Of course, we have talked about conversion electrons, but they are not so rare, at least at low energies. If the energy is high, of course, as in, let's say, many of these E0 states, then or states that decay by E0 transition, then of course the conversion electron process is also important. Then we have the E4 transition. We will see one case of that, and so on. Okay, so let me start by saying that the collective excitations in nuclei are of two types, namely rotational excitations and vibrational excitations. And of course, you can have a combination of these two. That is a more complicated kind of motion. We will stick to these simpler motions. And so, rotational excitation happens when a nucleus is deformed. The signature of such a behavior of a nucleus rotating collectively is that you have a rotational band with a band head, and the energies are roughly proportional to J into J plus 1, where J corresponds to the rotational angular momentum. So, of course, you can build this on intrinsic, so-called intrinsic states, which is single particle states, either, in a prolate nucleus or an oblate nucleus. And these rotations are usually associated with strong E2 transitions. If, of course, the spin is half integral, then you can have also M1 transitions, or the band head is non-integral, is integral in spin but non-zero, then also you can have M1 transitions, and they can compete with E2 transitions, and it depends on the structure of the nucleus whether one is favored or the other is favored. Vibrations occur when a nucleus, either it vibrates in terms of its density oscillations or in terms of its shape. You can have a E1 vibration, you can have a E2 vibration, E3 and so on. And these vibrations are usually characterized by a characteristic energy H cross omega. And so you have in the lowest order, of course, you have these excitation energies evenly spaced. You have you have a harmonic oscillator energy states. You have 0 H cross omega. Of course, 0 is 1/2 of H cross omega, depends on the number of degrees of freedom. And but if you subtract that out, then you just have E vibrational, 2E vibrational and so on. The low-lying vibrational states are, as I said, associated with the quadrupole oscillations or the vibrations where you have L equal to 3, which means E3 kind of vibrations. The high-lying vibrational excitations, of course, involve many nucleons, and then that is the so-called giant resonance. And why would we call it a giant resonance? Because it exhausts the full or a substantial part of the so-called sum rule strength. I have not defined this sum rule strength, but it is basically telling you, how much of the total strength is there in the E1 transition. And then that is distributed in among the low-lying states and this high-lying state. And in the case of, for instance, E1, it takes away almost all of the strength. So the so much so that the E1 excitations or E1 transitions are much weaker than even the single particle estimate. On the other hand, this is not true of the E2, and the E2 transitions are, for a well-deformed nucleus, are something like, and A equal to 150 nucleus. They are typically of the order of 200 or so of the single particle Weisskopf estimate. So the giant resonances, of course, are of many types, as I said, E0, E1, E2, E3, and then you can also have spin flip resonances, the so-called Fermi type or Gamow-Teller type, and these can also be delta T equal to 0, so isoscalar or isovector. So isoscalar is when the protons and neutrons are in phase, whereas if it is delta T equal to 1, then it is the protons and neutrons are out of phase. An example of this is the so-called monopole resonance, that is a delta T equal to 0 resonance, whereas the giant dipole, electric dipole resonance, that is a isovector. There is also, of course, a isoscalar that's a little more complicated. That's a kind of density fluctuation. But otherwise, the more well-known and well-studied E1 resonance is the isovector or delta T equal to 1 resonance, where the protons and neutrons are moving against each other and they are, of course, out of phase. Okay, collective rotations manifest themselves in as I said already, the characteristic low-lying energy spectrum. And this occurs in deformed nuclei, where the mean field is no longer isotropic in the rest frame of the nucleus. This is apparent in the low-lying states below, of course, the particle emission threshold, where Ex is less than separation energies for neutron, proton, and alpha, and so on. And they are discrete states. The rotational band based on the ground state, if J pi is equal to 0 for even nuclei, by even I mean even Z and even N of deformed nuclei, and these are best excited through the Coulomb excitation process using a high Z projectile beam. And the beam energy, of course, has to be chosen carefully. Namely, it has to be a little below the Coulomb barrier, so as to be unaffected by the strong nuclear force. Otherwise, you have a combination of Coulomb force and the strong nuclear force, and there are complications because the strong force then has to be modeled, and so what you extract then is a model dependent number from the experiment. Whereas if you stay below the Coulomb barrier, it's semi-classically just the Coulomb interaction that with some maybe a small, very small tail of the nuclear force, which you can make negligible if you go to about 90% of the Coulomb barrier. And this leads to a clean extraction of the transition probabilities, the E2 transition probabilities. And that is, of course, a measure of that is the so-called reduced transition probability, BE2. So, the Coulomb excitation process for the target or for the projectile, I mean, it works both ways because one is in the field of the other and so on, and vice versa. This can be thought of as being caused by a time-dependent strong electric field due to the, let's say, projectile, if you're exciting a target, and vice versa, as I said, due to a target if you're exciting a projectile. Now, as the low-lying E2 transitions are excited with a probability of the order of 1, if the BE2s are high and the excitation energies are low, then there is multiple excitation, because then this 0 to 2 plus, for instance, or let's say 3/2 to 5/2, that probability is of the order 1. So then while the projectile is moving, you can excite the next state and the next state and next state and so on. So typically you can go up to about 20 or 24 units of angular momentum that way in a rotational band. Of course, if you look at other states which are excited and which become, which are there, which are even lower than the partner states in this ground state rotational band, then those are not particularly well excited, because then you have to change you have to go from one band to the other, and that matrix element may not be large, so it is the ground state band is preferred by Coulomb excitation. The other more broadband method of excitation of low-lying excited states, rotational, vibration and so on, is using the heavy ion fusion reactions. So, in this case, the projectile and target fuse together, they form a compound nucleus after a while of the order of 10 to the minus 19, 20, minus 10 to the minus 20 seconds. And then this nucleus, by definition, if it's a compound nucleus, then it forgets how it was formed. It is rotating with the angular momentum. Of course, there is a distribution of this angular momentum of the compound nucleus, and the high angular momentum states will, of course, emit particles. Of course, all of them will emit particles, and then the high-lying ones will then decay by a series of gamma rays. If, of course, it is a low angular momentum, then of course there will be more of statistical emission before it comes down to the lowest states of a given angular momentum, so-called ERAS states. Okay, so this is a typical experimental setup. This is, of course, taken from a review article by David Klein in 1986, where you have an array of Compton suppressed germanium, high purity germanium detectors, and you have a beam coming in from the bottom. So the beam comes in from here, it is incident on a target, and then it makes Coulomb excitation of the target, and it scatters away, and then you can detect these scattered projectile like ions in these counters. They could be, for instance, parallel plate avalanche counters, or they could be multi-wire proportional counters, and so on. Usually one doesn't use silicon detectors because they get bad, they go bad very fast, especially with heavy ion bombardment. Okay, so usually these are gas detectors. As I said, it could be parallel plate avalanche, in which case you get a very fast timing signal. You can get position information, but you don't get energy information. If you have a multi-wire proportional counter and, let's say, backed up by another counter, then you can get a delta E. It's very difficult, of course, usually to get a E pulse as well, but you can get a delta E pulse, and so that might help in identifying other backgrounds and so on, or at least to distinguish between projectile and target. So you can use the timing information to distinguish between projectile and target, for instance. Okay, so the gamma ray spectrum, in coincidence with these gas counters which detect the scattered, inelastically scattered projectile, this is given here. As you can see, you excite a nice little band here up to about 14 units of angular momentum. They are nicely equally spaced. So you have I going to I minus 2, and so of course the intensity comes down partly because, of course, the angular momentum perhaps is not that high in this case, but partly also because the low-lying states are excited the most, and those are the stepping stones to the higher excited states, number one. And the efficiencies of the high purity germanium detectors also go down slowly with the increasing energy of the gamma ray. So here you can see also excitations of the xenon 136, and there are also excitations of the target. Okay, the other mode, as I said, and this is actually a very popular mode because it's a broadband way of exciting high spin states, that is the fusion reaction. And so there are a few pictures of this. This is taken from this excellent review article in 2016 by Riley, Simpson and Paul, and they show you a landscape of nuclei which has been studied using this very powerful method. So you can see that with spin, how the excitation energy goes up in 158 erbium, and there are different kinds of behavior that you see. You see collective rotation. Then there is also there are shapes various shapes which come in, and so on. and this captures that sentiment that you study the nucleus at from low to high angular momentum. And similarly here, this is shown the work that was done using more modern arrays, which are gamma ray tracking arrays such as Greta and Agata. So Greta is the US array and Greta Agata is the basically European array, and these are the earlier arrays, the Tessa and Hera. Okay, so these actually studied this region, whereas the newer arrays go up to higher angular momenta, in fact to the limits of the maximum angular momenta. I don't have a picture here, but maybe I'll show it in some future lecture. The using a semi-classical phenomenological model of the nucleus, basically liquid drop, in the mid 70s, Plazil and Swiatek actually found and they followed, by the way, Chandrasekhar's idea on how fast can a gravitating object spin. So they extended that to a strongly interacting systems such as the nucleus, and the conclusion was that in the A120 or 130 region, the nucleus can accommodate the highest angular momentum, and that is of the order of 80 units of h cross. In lighter nuclei, this comes down very much, and also in the heavier nuclei. So you have a kind of distribution which is peaked at around the highest angular momentum is the largest in nuclei around A120 or so, and then goes down on either side. Of course, in the heavier side, it is the highest angular momentum is also limited by the fact that it undergoes fission. So faster it spins, it more easily decays. It cannot sustain it for long, and it fissions. Okay. So anyway, these are examples of gamma ray spectra. You can see that the early measurements using sodium iodide detectors were limited to this kind of spectrum. Only a few of the states could be seen. Then when you went to germanium detectors, then this was extended, and when you had a larger array, this was extended further. But so this is Tessa, and then of course if you have gamma sphere, which has about 100 odd high purity germanium detectors, then you can extend this spin considerably. Okay, and also with good statistics. This cartoon shows how you can make a high spin nucleus. So you take a projectile and a target, and then this fuses, and then there is particle emission, proton, neutron, and so on. Of course, to a much smaller extent, gamma ray emission as well. And for instance, that is used to study the giant dipole resonance in excited and rapidly rotating nuclei. But that's a very small branch. It's a branch of the order of 10 to the minus 4 of the particle emission branch. Then of course, once you have evaporated particles and you have come down below the particle emission threshold, then you only have gamma ray emission. So initially you have some statistical emission, and then when you go down to the lowest bands, then you have a cascade of these transitions, which one of these are examples of that. And then ultimately you come down to the ground state. So this happens, this kind of de-excitation happens in the time scale of picoseconds, or even somewhat smaller than that. As you come down, of course, the time scales slowly start increasing. You get hundreds of picoseconds and then nanosecond and so on. If there are isomers, of course, they can live much longer, and that can happen if you get caught in a state which has a very different structure from the nearby states. Okay. Just as you can have Coulomb excitation with beam energies of the order of 5 MeV per nucleon or less, you can also have relativistic Coulomb excitation at beam energies of the order of 1 GeV per nucleon or even higher. So what happens here is that as the high Z projectile flies by the target feels a pulse of the electromagnetic field with a frequency cutoff. Within a semi-classical picture, you can actually calculate this cutoff as being h cross c, I mean, the energy cutoff can be given by h cross c by gamma times b, where b is the impact parameter. It's a semi-classical picture, okay, and gamma is just the total energy divided by the rest mass of the projectile. So, for a proton, for instance, a 1 GeV proton, this would be about 2, but 1 GeV per nucleon is okay even for heavy ions. So, this gamma would be of order 2 for 1 GeV per nucleon, but of course, if you go to higher than that, then this time dilatation factor increases, and then you go up to higher frequencies. Okay. So, this was the method used to actually excite 1 and 2 phonon giant dipole, electric giant dipole resonance, and also observing the de-exciting gamma rays. And they were measured in coincidence in a TAPS array. So, they had about 4 walls, I think, of barium fluoride detectors, and shot bismuth 209 on lead 208 and looked at these collisions. So, these bismuth scattered particles were detected, and of course, the gamma rays were detected here. So, and since these are fairly close in A, of course, you can have excitation of bismuth as well as lead, but then you Doppler correct, because these are happening at large impact parameters. So, if it is from the moving bismuth, then of course there is a certain Doppler shift and a Doppler broadening depending on the angular acceptance of each of the elements of the detectors. If it is from lead 208, then of course it is due to the moving recoiling 208 lead, and that also leads to Doppler. So, they have done this experiment such that they correct for this by detecting these scattered particles as well as the target nuclei. And so, this is what is shown here is the excitation of the single giant dipole resonance. So, you can see a single peak here. This is a double, let me see, this is a single peak, and this is also a single peak. So, this is a 1 phonon excitation of the giant dipole in 208 lead, whereas this figure shows you the 2 phonon excitations. So, you can see that this peaks at around 24 MeV or so, okay, 24, 25 MeV. So, the cross section for the 1 phonon excitation is of the order of as large as 5 barns, okay. So, because after all these are peripheral collisions, and the cross section is an integral from let us say B min to B max, but with a B weightage on it. So, 2 pi B dB, okay. So, this is the cross section for 1 phonon, and for 2 phonon, of course, since it is a fast collision, it has to excite the next phonon. So, that probability is smaller, and this cross section is about maybe 6 times or 6 to 7 times smaller than the 1 phonon excitation, but it is still quite sizable at about 0.8 barns. The widths of these resonances are given here. The width is of the order of 13 MeV, and with an error, this is the error, 0.1 error, and these are the energies of the resonance, the double resonance 25.6 with a width which is this 5.8 plus minus 1.1. So, relativistic Coulomb excitation, of course, is a very powerful technique to study very high lying excitations. And the picture is the following, and this is taken from this review article, Physics Reports, actually the thesis of Bertolani. So, this is the semi-classical amplitude for exciting the E1 giant dipole versus E lab by energy per nucleon. So, as you can see, at 1 GeV per nucleon, it is already close to saturation, and that is of the order of about 0.6 or so. Okay. So, this is the amplitude, and so the picture is like this. The projectile comes in here, and the target feels a transverse field as it just zips by, and this is compressed because of the relativistic dilatation factor. Okay, so this is the photoabsorption cross section, and this also shows the giant dipole resonance. It is split in the case of 150 neodymium because, so the energy is of the order of about 20 MeV or so, but the splitting of this arises because for a deformed nucleus there are basically two directions. One is the in a prolate case, for instance, you have a long axis which leads to a lower resonance energy, and you have a short axis, and there are two short axes in a prolate nucleus. So the strength is more, in spite of the fact that its width is also more. So you have this kind of splitting, and you can infer about the shape of the ground state of this nucleus. You can see that this is very different from lead 208, which is a doubly closed shell nucleus, and there is single peak which peaks at about 13 odd MeV, and this is one peak. So because all directions are the same. Similarly, you can excite this not just by photoabsorption, you can excite it by hadronic means. You have a proton of 400 MeV, then you excite various kinds of multipoles. You have the isoscalar giant quadrupole resonance, then the isovector giant quadrupole resonance, and these can be deciphered by actually doing the experiment with alpha particles, which is a isoscalar object, and there you will only excite the isoscalar giant quadrupole resonance, not the isovector. So there are ways in which you can disentangle the isovector and the isoscalar components. So this is a picture of the giant dipole resonance. You have the protons and neutrons oscillating against one another, and they involve the coherent excitation of the electromagnetic modes. The electric modes involve oscillations of the charge with respect to the center of mass against the neutrons. For example, in the case of the delta T equal to 1 giant dipole resonance, or even spin excitations. And these E1, E0, E1, E2 have been measured. They correspond to L equal to 0. So the angular momentum associated with these resonances is 0, 1 and 2 respectively. And the isoscalar modes can be excited by any hadron and lepton, but the isovector modes can be excited, at least to lowest order, by only T equal to 0 projectiles. Okay, sorry, there is a mistake here. The isovector modes cannot be excited by T equal to 0 projectiles, such as the alpha particle. Okay, they can only be excited by T equal to half, or T equal to 1, T equal to 3 half projectiles. The E0 breathing mode, where the nucleus actually just there's a radial oscillation with respect to the density, and that can be related actually to the nuclear compressibility, and this is crucial in stellar matter calculations, including supernova explosions. Similarly, there are, as I said, spin isospin giant resonances. So the photoabsorption excites mainly the E1, very weakly the M1 states. The spin flip resonances can be excited, as I said, by PP prime at low momentum transfer, and backward EE prime inelastic scattering. If you want to excite the spin isospin resonances, then of course you have to use non-zero isospin projectiles. So, and the reaction channel that are normally used are the PN reaction, or the helium-3T, or the NP, 7 lithium, 7 beryllium, and so on. One interesting finding is that the Gamow-Taylor resonance, where delta S equal to 1, delta T equal to 1, is damped, and the missing strength is spread over a very large energy region. These reactions, spin isospin excitations, using these such projectiles, such reaction channels, they have also been used to excite the free delta resonance, that means on a proton, but also bound state delta resonances in nuclei. Okay. Now we will talk about some rare electromagnetic transitions. As I already said, the E0 transitions in oxygen, for instance, in oxygen 16, where the 6.05 MeV state has a lifetime of about 67 picoseconds, and the E plus E minuses can be measured with the magnetic spectrometer, but you can also measure the 2 photon decay channel using appropriate high energy gamma ray detectors. Then there are these K forbidden decays, the projection of the angular momentum along the symmetry axis, that is we saw that as omega, but that you can sometimes the K symbol is also used for that. And if you have a state which has a very high K and the nearby states have a very different K, then you have hindrance in the decay, and so the lowest such high K state can be isomeric. And in fact, this, if I remember right, this is of the order of 30 years. I should have written it down here. But in hafnium-178, the K equal to 16 isomer at 2.5 MeV roughly is having a very large half-life. I think it's of the order of 30 years or so. Pair decays, of course, have been observed from 0 plus to 0 plus transitions in carbon 12 and oxygen 16. Similarly, there are also, just as you have K isomers, you have shape isomers. And this can happen where you have heavy nuclei with a second minimum, as we saw in an earlier lecture. And if a nucleus exists in the ground state in the second well, then of course it can either fission or it can decay through gamma ray decay. But then if it decays by gamma rays, it has to come back to the first well. And since there is a small overlap between these two structures because of the large difference in the shapes, that is usually these states are isomeric, but these have been measured in a few cases. Then I will come to one very rare electromagnetic transition. There is a low-lying state at just, of the order of 10 electron volts in 229 thorium. That, of course, lives for a very long. It's isomeric. And this has been measured recently, about a few years ago, and is a candidate for the nuclear clock because the state which decays is very sharp because it's isomeric, and similarly the ground state, of course, is very sharp because the only way it can decay is by alpha emission. That is of the order of thousands of years. So this is a candidate for this, and a lot of work has been going on in this area, looking at this 229 thorium. In principle, since there is only 8 electron volts, we could excite this state using very strong laser beams as well, and that is how probably ultimately we might make a nuclear clock. Okay, now I will come to this E4 transition in 60 nickel. As you can see, cobalt 60 is a very standard gamma ray calibration source used in low energy nuclear physics, and the ground state decays predominantly. Okay, this is what is shown is for this decay, but the ground state, I should have taken another figure, maybe I'll replace it in the ultimate slide. The ground state decays to the 4 plus state, which is at about 2505 MeV. Maybe I should write it down here. So there is a state here at 2505 keV, and this is the 4 plus state, and the ground state actually decays almost 100% to that state. Okay, so the E4 transition that I am talking about is the transition from this 4 plus state to the right up to the ground state. The usual way it decays is that it decays to the 1332 keV state and then that decays. So there is a cascade of 2 gamma rays, and so the 1173 and 1332 are used as calibration for any of the low energy gamma ray detectors. This experiment actually looked for the E4 transition, and how did they do that? If you put any detector, it would of course be swamped by the 1173 and 1332 keV gamma rays. So a smart idea was to actually put a very strong source in heavy water. Now heavy water of course has deuterium, it's D2O, and deuterium has a breakup threshold of about 2.22 MeV, 2.225 MeV. Okay, so if this transition takes place, then that can break up a deuteron and produce a neutron and a proton. Now the free neutron, it has of course hundreds of keV energy, couple of hundred on the average. Then that will get thermalized in this heavy water by making a series of elastic collisions, And then, of course, the cross section for getting detected in a BF3 counter increases dramatically because you have a broad resonance in boron. And so that's how then, if you have a BF3 proportional counter, then you can detect the neutron in this. So this is the BF3 counter, uh, and this is used for other purposes of calibration and so on. And of course, the whole detector is shielded using lead surrounding it, and you look for the neutrons. Now, of course, you can get this thermal neutrons from cosmic rays and so on. So that they have seen is a very small background. Similarly, from there are gamma ray sources outside, and they also contribute to a very small extent. So this experiment actually measured the branching ratio of the E4 as compared to the normal decay via 2 gamma rays, and this branching ratio is found to be about 2 with a 20% error bar into 10 to the minus 8, and this is only about 17% of the single particle or Weisskopf unit strength. These are some details of the source, about 45 Curie source, very strong. The count rate of the from the cobalt for this E4 transition was about 17 with a background of about 7. And there is another excited state in nickel 60 at 26 keV, but that population is probably very small, and that transition has been neglected, of course, in this analysis. This is the reference for that. Okay, so in summary, we have discussed briefly, of course, some aspects of the population and study of collective states by Coulomb excitation, low energy as well as high energy. So less than 5 MeV per nucleon, greater than or of the order of 1 GeV per nucleon, and also by fusion evaporation reactions. The electric and magnetic giant resonances are a general feature of nuclei and are excited by suitable probes and suitable reactions. Finally, we discussed some rare processes such as pair decay and E4 decay in 60 nickel. Thank you.